So this R value, I'll put it here, R is 8 centimeters. It's just over 1/4 of the full radius. Okay, so basically, when the electric field is going from bottom to top, we want to see what magnitude of the magnetic field is going around a central, we'll say, cylinder of that radius, lowercase r. Okay, so let's see. The full Maxwell's equation for, or that includes the displacement current, is integral B dot ds is equal to mu naught times ID, which is the displacement current, right? And so embedded in here is the magnetic field, and we're saying that that is directly equal to, or rather directly related to, the electric field, specifically a changing electric field, right? Mu naught is then epsilon naught d phi e dt, right? Right here, this tells you that the magnetic field B is directly related to the electric field here that's changing in time, right? The electric field magnitude is embedded in the flux right there of phi. Well, if that's changing, that's creating a magnetic field. So let's see what that value is. Okay. All right. So we have B, the ds rather. Tell you what, let me write that, I guess, scenario from a top-down view, right? So here's the upper plate, if you will, the upper plate, and then we have that small circle of radius r, like that. The electric field is coming up towards us, which means it's like that. That's also the direction of the current. Okay, so using the right-hand rule, put your thumb, say, out of the screen. That means your fingers will curl in the counterclockwise direction. That will be the direction of the induced magnetic field. Okay, so let's see what that value is. That ds, right, the path length, is, well, the circumference of that circle. So 2 pi times lowercase r. Right, that's the path of that enclosed, or that closed loop. So that equals mu naught epsilon naught, and again we have this d phi, right? I guess you can use the displaced current again. Actually, let's do that. This ID here, we can't use the displacement current that we found in previous parts, right? Because that was for the entire capacitor. Right now, we just want to find the displacement current just in that tiny region, because that's the current, that's the displacement current that will create this magnetic field. So what I mean is that a displacement current I'll call I prime divided by the area of that tiny circle is proportionally equal to the displacement current of the entire capacitor over the entire capacitor's cross-sectional area. Right? So primed equals unprimed. And so this gives us an expression for our displacement current in just that tiny region. Specifically, A prime over A times I. Okay? And this equals pi r squared divided by pi capital R squared, right? This was capital R, and ID, okay? By the way, this unprimed displacement current is, or what, I can't talk, was what was, there we go, was what was stated in the problem, okay? So now we can take that expression and plug it in right there, such that we have the following. The pi's cancel out. We have r squared divided by capital R squared times ID. And now getting an expression for B, we actually have mu naught. One factor of little r goes away. So mu naught r id over 2 pi capital R squared. Right? And so now we know everything. We can plug in our numbers. Mu naught has a value of 4 pi times 10 to the minus 7, I believe. Yes, minus 7. Little r was 8 centimeters or 0.08 meters. Displacement current was our 9.1 times 10 to the minus 6 amps divided by 2 pi. Capital R was 29 centimeters, so 0.29 squared. And after all this, we should get a value of 1.7 times 10 to the minus 12. The units, Tesla. Teslas. All right. So the trick, at least for part D, was realizing that we could not use the displacement current in our expression right there because we only wanted the magnetic field that was generated in a small percentage of the area, right? Thus, we had to come up with some, I guess, relationship, right, between the two displacements, or rather the two displacement currents, okay? So keep this in mind. Otherwise, that's it, right? This is the displacement current for a changing electric field that induces a magnetic field. Thanks for watching.